Now, if we move to mathematical induction. Now, mathematical induction is just another type of proofs, but here in which you use assumptions unlike direct proofs. Now, in mathematical induction, you'd have a given statement in terms of n. So over here, we have a given statement in terms of n, which we want to prove true for all n. Now, here are the 3 steps to follow in order to prove a statement by mathematical induction. Now, in step 1, you prove that the statement is true for the first value of n. Now, if you're given to prove that the statement is true starting from n equal to 5, for example, then here in step 1 you prove it true for n equal to 5. If you're asked to prove it true for all natural numbers, then your first value of n is 0. Now, why is it that this step is useful? Now, you could ask me, why not immediately start from step 2? Why not skip checking it true for the first value of n, for example? Now, it's because that if the statement is not true for the first given value of n, then there's no point to move forward with the proof. You just stop it there and say that the statement is false. So if it's not true for the first value of n, then therefore it cannot be true for all values of n. But when you verify true for the first value of n, you may move on to steps 2 and 3. Now, in step 2, you suppose that the statement is true for n equal to k, where k is greater than the first value of n. Now, this is the assumption we spoke about earlier. You assume it true up to rank k, and you try to use that assumption to prove it true for the next rank, which is n equal to 1, which is basically step 3. Now, why do we do that? Why would steps 2 and 3 help me prove that the statement is true for all n? Now, suppose we have a sequence here. Suppose we have u1, u2, u3, u4, etc., up to uk plus 1, etc. And the sequence keeps on going infinitely. Now, based on steps 2 and 3, if the statement is true for u1, where k is equal to 1, then it's true for k plus 1, which is 2. Then the statement is true for u2. And if it's true for u2, where k is equal to 2, then basically it's true for k plus 1, which is 3, then the statement is true for u3, etc. If it's true for u3, where k is equal to 3 here, then the statement is true for k plus 1, which is 4, then the statement is true for u4, etc. Then for any k, the statement is true for k plus 1, therefore we'd have it true for all values of n. Now, let's just put this into an example here. Now, I'm going to solve example 2 before example 1 because example 2 is slightly easier. Now, we have this conjecture here. We have the statement in terms of n. So, if we look at the first side here, the first side is expressed using sigma notation. Now, if using sigma notation in the proof is a bit confusing for you, it's no big deal. You can just expand the sum. If, for example, we expand it here starting from r equal to 1 to r equal to n. So for r equal to 1, I have an 8. For r equal to 2, I have 2 into 4 plus 6, which is 20. All the way to r equal to n, which is n into 2n plus 6. So this is basically the sum I have on the first side. So on the other side, this is what I need to prove the sum equal to. I need to prove that the sum on the left-hand side is equal to 2/3 of n into n plus 1 into n plus 5. So according to the 3 steps of mathematical induction, in step 1, I need to prove the statement true for the first value of n. Now, what is the first value of n here? The first value of n is basically 1, because we started with r equal to 1 all the way to r equal to n. So here in step 1, I want to prove the statement, which I call 1. So I want to prove 1 true for n equal to 1. So for n equal to 1, on the first side, I have an 8, which I want to prove it equal to the right-hand side for n equal to 1. On the right-hand side, for n equal to 1, I have 2/3 times 1 times 2 times 6. So when we simplify the other side, I end up with an 8. So 8 is equal to 8. This is true. Therefore, 1 is true for n equal to 1. Since I've proven this statement true for the first value of n, now I can move on to step 2, which is making my assumption. So in step 2, I assume, or I suppose, 1 true for n equal to k, or up to rank k, which means, i.e. means, which means that 8 plus 20 all the way to k into 2k plus 6, we're just replacing here n by k, is equal to 2/3 of k into k plus 1 into k plus 5. So I do have this true, and I want to use this to prove that the statement is true for n equal to k plus 1, which means over here I replace n by k plus 1 in order to determine the statement that I want to prove here in step 3. So it's 8 plus 20 plus rank k, which is k into 2k plus 6, and I add to it rank k plus 1, which is, I replace n by k plus 1, which is k plus 1 into 2 into k plus 1 plus 6 gives me 2k plus 8. Over here, what I did is basically replace n or r here on the first side by k plus 1. So I end up with k plus 1 into 2k plus 2 plus 6, which is 2k plus 8. And I do the same thing on the right hand side. I replace n by k plus 1. So I end up with 2/3 of k plus 1 into k plus 2 into k plus 6. So this is the statement that I want to prove true using the assumption I've made in step 2. Now if we open up a new page here, I'm going to rewrite the statement that I need to prove true. I want to prove that a plus 20 plus k into 2k plus 6 plus k plus 1 into 2k plus 8 equal to 2/3 of k plus 1 into k plus 2 into k plus 6. So this is the statement I want to prove true. So if we look at the left-hand side, what I'm going to start with, if you look at those terms, those are basically the sum that I assumed equal to the statement they needed in step 2. So if you see here, I have that those terms are basically equal to 2/3 of k into k plus 1 into k plus 5. So this is where we use the assumption. So over here, 8 plus 20 all the way to k into 2k plus 6, I can basically replace by 2/3 of k into k plus 1 into k plus 5. And I just add to them the remaining term, which is rank k plus 1 plus k plus 1 into 2k plus 8. And I need to prove that this sum is equal to the left-hand side eventually. Now, if we look here, I have a k plus 1 and a k plus 1, which is a common factor, and I have a k plus 1 here in the statement I want to reach. So basically, I also notice that I have a 2/3 here. So when I look at the statement I already have, I do have a 2/3 on the first side, but I do not have a 2/3 in the other term. So this is why I can get it 2/3 by multiplying by 2/3 and multiplying by its reciprocal, because 2/3 times 3/2 is 1. So basically I wouldn't be changing the statement. It's very important not to change the statement. So now I have a 2/3, which I can also factor out with the other common factor, which is k plus 1. So I end up with 2/3 into k plus 1 factored out into the remaining terms, which are k into k plus 5 plus 3/2 into 2k plus 8. I simplify the terms in the brackets. I end up with k squared plus 5k. 3/2 times 2k is 3k. 3/2 times 8 is 3 times 4, which is 12. So by simplifying those, I end up with 2/3 into k plus 1 into k squared plus 8k plus 12. Now here, I need to factorize the quadratic factor. I want factors of 12 whose sum is 8. I do know that I have 2 times 6, which is equal to 12, and 2 plus 6 is equal to 8, so therefore those are the two factors I need. So it's 2/3 into 2k into k plus 1 into k plus 2 into k plus 6. Therefore, if you compare them, if you compare this with the statement here, you notice that they're the same. Therefore, I have reached the statement I want. So basically, I've proved it true for rank k plus 1. So then 1 is true for n equal to k plus 1. Then 1 is true for all n in z plus. Now, over here, why am I taking z plus? Because if you go back here, you notice that sigma starts from, r starts from 1 to n. So basically those are all natural numbers except 0. And all natural numbers except 0 are denoted by z plus. So z plus is the sum, it's the set that contains 1, 2, 3, etc., all positive integers, all non-zero positive integers. So this is for this example. Now we could go back to example 1. Now example 1, I want to prove the following statement by mathematical induction as well. So over here, if we look at the given values of n, we notice that they want me to prove the statement true for all n greater or equal to 8. So here our first value of n is 8. So in step 1, I want to prove the statement, which I call 1. So I want to prove 1 true for n equal to 8. So I start with each side of the inequality apart. So for n equal to 8, n squared is 8 squared, which is 64. And the other side, 7n plus 1, for n equal to 8 is 7 into 8 plus 1, which is equal to 57. You notice that 64 is greater than 57, then 1 is true for n equal to 8. Now, in step 2, I assume that 1 is true for n equal to k, which means that I replace n by k in the statement, which means that k squared should be greater than 7k plus 1. And of course, in step 3, I want to prove 1 true for n equal to k plus 1, which means, so I replace n by k plus 1. I always urge you to write what each step basically mean for the statement. Always write down the statement in terms of k and in terms of k plus 1 in order to be able to see what you have and what you want to reach. So over here, this means by replacing n by k plus 1, it's k plus 1 all squared greater than 7 into k plus 1 plus 1. So this is the statement that we want to prove. Now k plus 1 all squared is equal to k squared plus 2k plus 1. So you notice that in k plus 1 all squared, I have a k squared, which in step 2, I know that k squared is greater than 7k plus 1. So, by taking k squared greater than 7k plus 1, in this inequality, the inequality I have drew from step 2, in order to reach k plus 1 all squared, I need to add to k squared, I need to add 2k plus 1. So we know that whenever we add the same number to both sides of an inequality, the inequality is unaffected. The order of the inequality remains the same. So k squared plus 2k plus 1, I just add 2k plus 1 to both sides, is 7k plus 1 plus 2k plus 1. So on the first side, I do have k plus 1 all squared. Now, on the other side, before I jump into simplifying the expression and grouping similar terms and adding them together, I look at the statement that I want to reach. If we look here, I have that 7 into k plus 1 plus 1, which basically is 7k plus 7 plus 1. So over here, I already have a 7k. So I need a plus 7 next to it in order to reach 7 into k plus 1. So where could I get that 7 from? I look at this one here. This one, I can write it as 7 minus 6, right? So that's simple. So I end up with 7k plus 7 plus 1 plus 2k minus 6. So k plus 1 all squared is greater than, I factor out the 7. This is 7 into k plus 1 plus 1 plus 2k minus 6. So if you look at that statement, 7 into k plus 1 plus 1, I already find it here. But I do have a 2k minus 6 added to it. It's no big deal since over here we just want to prove k plus 1 all squared greater than it. So all we have to do is basically check if 2k minus 6 is a positive number. If 2k minus 6 is a positive number, then when you add it to that statement I underlined in blue, you would get even a greater number. Now, what do I mean? So, let's just start by proving 2k minus 6 positive. Now, what do I know about k? We've seen that when you assume it true after rank k, k should be greater than the first value of n. Now we know that the first value of n is 8. So over here, k is greater than 8. Then 2k is greater than 16. Then 2k minus 6 is greater than 10. Since 2k minus 6 is greater than 10 for all k, then 2k minus 6 is a positive integer. Fine. Now that we've proved that 2k minus 6 is positive, I'm just gonna finish the proof up at the top here. So, since 2k minus 6 is positive, then 7 into k plus 1 plus 1 plus 2k minus 6 is greater than 7 into k plus 1 plus 1, right? If you have a number a, if you add a number positive to number a, you'd get an even greater number. And according to the statement that we have here, we have that k plus 1 all squared is greater than 7 into k plus 1 plus 1 plus 2k minus 6. So by transitivity, if a is greater than b and b is greater than c, then definitely a is greater than c. Therefore, I conclude that k plus 1 all squared is greater than 7 into k plus 1 plus 1, so which is the statement I wanted to prove for rank k. Then I deduce that 1 is true for